Hello and welcome to my science tutorials. In today's video we are going to be looking at units of measurement and dimensional equations. So without further ado, let's get started. So first of all, before we start with dimensional equations and dimensional findings, we need to first of all look at what an SI unit is, a base unit, derived unit, and then what dimensional equations are. So an SI unit simply stands for System International, and this is a standard unit of measurement that is understood and accepted by scientists all around the globe. So to avoid confusion between scientists, the SI unit system of giving units to quantities was adopted, and then all scientists have agreed to it. So if the unit of measurement which of length, which is meters, is meters in, let's say for instance in America, it should be meters in Africa, meters in Europe, and then meters anywhere else on planet Earth. So this system of unit measurement brought understanding among scientists all around the world. So with that being dealt with, let's look at what a base unit is. So base unit, these are fundamental units from which all other units are derived from. So they are fundamental, they are more like the core of all units. Okay, so a combination of two or more fundamental units or base units will give you a derived unit. And then here are some few examples of some of the base units that we have. So we have length, which is measured in meters, the SI unit is in meters, and then mass in kilogram, time in seconds, thermodynamic temperature in Kelvin, electric current in ampere, luminous intensity in candela, and then amount of substance in mole. And then these are their symbols. Now take good note of the symbols. Okay, the meters is small m, and then the kilogram is capital K and then small g. Okay, the seconds is small s, and then the Kelvin is capital K. Electric current, the symbol is capital A for ampere. So let's take note of this symbols when we use them as the units of quantities. So now let's have a look at what a derived unit is. So a derived unit, these are SI units obtained by the combination of two or more base units. Okay, so some examples of quantities that have derived units include force, work, power, and resistance. Okay, so with this fundamental bit dealt with, let's look at what a dimensional equation is. So a dimensional equation is an equation that expresses a physical quantity in terms of its dimension. So if we have a physical quantity and it is being expressed in its own dimension, then we said that dimension is what a dimensional equation. Okay, so we have here the three fundamental units that we use in dimensional analysis include the mass, length, and time. So the mass has the dimension of m, so it starts with mass m, so it has the dimension of m. Length has the dimension of l, and then time has the dimension of t. Now mind you, length and breadth and height all are distances and they are all lengths. So when we have breadth, length, or height, it is still l. The dimension of that breadth or length or height in dimensional analysis is still l, irrespective of whether it's breadth, height, or length, is still l. Now to show that we want to find the dimension of a particular quantity, we use these two brackets over here, the straight ones over here. We use them to symbolically represent the dimension of a quantity. So for instance, if I have into bracket these two brackets open and I have the length, this implies the dimension of length. Okay, so if I have this and I have the length inside, it means I have to write L as my answer. So that is the dimension of length. Okay, so let's have a look at some few quantities and then their dimension. Okay, so the first one we want to look at over here is speed. Okay, so let's look at speed. Like I said, to find the dimension of speed, we need to put it into this bracket. Okay, so speed is given to us by what? Distance over time. Now velocity on the other hand will be what? Displacement over time, but they are all what? Distances, and they are all lengths. Okay, so we have here, we put them into this bracket to show that what? We want the dimension of these two quantities. Now the distance is what? it's a length, okay? So it has the dimension of L, and then time has the dimension of T. So the dimensional equation for speed is what? LT minus 1. Let's have a look at another example. Area. The dimensional equation for area. So area is what? If you have, like, you have to find the area of a box or a cube or a rectangle or a square, sorry, a rectangle or a square, you normally use what? The length multiplied by the breadth, okay? So to find the dimensional equation for area, you just need to find the dimension of length multiplied by the dimension of breadth. And like I said earlier on, length and breadth, they are all distances, okay? So in dimensional analysis, you represent them with L. So we have L times L, which is what? L squared. Now let's have a look at another example. Density. Now density is defined as what? Mass over volume, okay? So we have the dimension of this. Now mass is capital M, okay, divided by, now volume of a substance is what? The length times the breadth times the height, okay? Now the length, the breadth, the height, they are all distances, okay? So instead of having length times breadth times height, we are going to be having what? We will have length times length times length, because they are all lengths or they are all distances, okay? Then we have M at the top over here. So at the end we will be having M, then the denominator over here will be given as what? L cubed. So you have ML minus 3. The L, when this comes to the top, it becomes negative, so we have ML minus 3. Okay, so this is the dimensional equation for density. Now let's have a look at acceleration due to gravity, or just a normal acceleration. So for acceleration, we have acceleration to be what? Velocity over time. Hey, sorry. Velocity over time. So the dimension for velocity and then the dimension for time. Now velocity is what? Distance over time. So let me use D for the distance divided by time all over what? The dimension for time again is time, okay? Now the distance, like I said, is L in terms of dimensional analysis. So we have the top, which is for the velocity, will be what? LT minus 1 divided by T again, okay? So if this T comes to the top, we will have what? LT minus 2 as the dimensional equation for acceleration. Okay, so let's have a look at more examples. So let's have a look at force. Okay, now force is given to us by what? Mass times acceleration. Okay, so to find the dimensional equation for force, we multiply what? Mass by acceleration, and then mass is capital M times acceleration is what we find at the top over here is LT minus 2. So we multiply it with LT minus 2. So in the end we are getting what? MLT minus 2 as the dimensional equation for force. Let's have a look at one final example, and then we go to the uses of what? Dimensional analysis. So the final one we want to look at over here is pressure. Now pressure is given to us by what? The formula force over what? Area. Okay, now the force, okay, the dimensional analysis or the dimensional equation for force is what we have over here at the top, which is what? ML minus 2, MLT minus 2. And then the area, as we found earlier back, was what? Length times breadth, which is what? L squared. Okay, so at the top over here we'll be having MLT minus 2. Then the L square will come to the top, will now become what? L minus 2. Okay, we have one L here, one L here, so we have what? ML minus 1, T minus 2. So this is the dimensional equation for pressure. Now, so why do we need to study dimensional analysis? Why the need for all this MLT minus 1 and other stuff? Well, it so happens that dimensional analysis has some very useful uses, okay, and we are going to look at these uses very soon. So let's look at some uses of dimensional analysis. Now, one, dimensional analysis can be used to find units of quantities. So we can use them to find units of quantities. Okay, so by units of quantities, what do we mean by this? Remember we said for density, the dimensional equation is what? ml minus 3. Okay, so if this is the dimensional equation, we can get the unit from this. Okay, we know the m is what? The mass, and then mass is measured in what? Kilograms. Okay, we know the l is what? The distance. Okay, and distance is measured in what? Meters. So we have meters cube. So this is the SI unit for what? Density. So if you know let me put density here. So if you know the dimensional analysis or the dimensional equation of a particular quantity, from that dimensional equation you can get what? Your SI unit. Just as simple as that. So this is one of the uses of dimensional analysis. Now, two, it can be used to find what? An equation between quantities. Okay, so it can be used to derive equation between quantities. Equation between quantities. Now, what do we mean by this? Equation between quantities. This simply means whenever we have, let's say, force, and it depends on maybe the length, the density or something, we want to know how they are related. Okay, whether they are directly proportional or inversely proportional, or they are directly proportional to the root or the square of any other quantity. This way of deriving relationship between quantities, we can use dimensional equation or the dimensional analysis to find this relationship between two quantities. We will be looking at this into much more details very soon, so don't worry if you don't understand. You'll still get it at the end of this video. So finally, it can be used to check the validity of an equation. Check the validity of equations. So if you have any equation and you want to know whether the equation is valid or not, okay, you can use dimensional analysis to check for the validity of this equation. Now let's now appreciate the fact that we said we can use dimensional analysis to what? Derive an equation between quantities. So let's have a look at how we use dimensional analysis to derive an equation between quantities. Okay, so let's have a look at example 1. So let's try example number 1. So the example number 1 is telling us the period of oscillation of a simple pendulum depends on the length L of the thread, mass m, and then acceleration due to gravity. Using dimensional analysis, derive a formula for the period of oscillation. Now let's have a look at the quantities we have in this question. So first of all, we have period. Okay, so now period is just time. Okay, so period is time. So the dimensional analysis for, or the dimensional equation for period will be t. Now they say it depends on the length. Okay, so we have length, and we know the dimensional equation for length is still L, so that one no problem. Mass, we also have mass, and we know the dimensional equation for mass is still what? Capital M. And then we have acceleration due to gravity. Now acceleration due to gravity, we represent that with G. Now acceleration due to gravity is just simply like acceleration. It has the same dimensional equation as acceleration, and acceleration we saw earlier on was what? It has the dimension LT minus 1. Okay, sorry, LT minus 2. Acceleration is velocity over time, and then that will give us LT minus 2. Now with all of this now obtained, we can go ahead and then solve the question. So how do we now start? Okay, they are saying the period of oscillation of a simple pendulum depends on. So whenever something depends on something, we use the proportionality sign to represent that, because we don't know how they depend on each other. So it depends on the length, so we have L over here, then the mass M, then what? The acceleration due to gravity G. Okay, so now the period, okay, is equal to, now if we remove the proportionality side, we introduce a constant, so we write k over here, then we have L, M, and then we have what, G. Now we don't know how these quantities are related, so we give them a power. Okay, let's say x, y, z. So we need to find the value of x, y, and z. From these findings, we can now determine how the period of oscillation depends on the length, the mass, and then the gravity. So from here, we have, this shows that the dimension of period. So instead of writing into bracket p, we write t after this point. So we have the t is equal to the constant. Then this will be what, Lx, because the dimension of length is still L, that of mass is still y, and then that of gravity is what, Lt minus 2, then the power z. Mind you, this is the power y, so it's not my. Okay, sorry about that small writing. So we have here t is equal to what, k, L power x, m power y. Then we expand this bracket, we have L power z, t power negative 2z. Okay, so from here we can see we have L here, L here. So let's simplify that further. We have t is equal to k, L power x plus z. Okay, they have the same base, so we add the exponent. So we have m power y, then t power negative 2z. Okay, now from here we compare powers, comparing powers. Okay, now by comparing powers, we mean whatever we have on the right hand side over here, if we have it on the left hand side, if we have it on the right hand side, okay, then we compare their powers. Okay, so the first thing we have over here is we have t here, so let's compare the powers of what, t first. If we are comparing the powers of t, we can see this t has the power of 1, so 1 will be equal to what, the negative 2z over here, so negative 2z. Okay, so this implies that the value of z over here, we divide both sides by what, negative 2, we get negative 1 over 2. So this is the value for our z. Okay, now comparing powers of what, m. Okay, because we don't have any m over here, we assume the power of the m over here is 0, so m raised to the power 0 is 1. That is how come the m is not here. So it means what, our y is equal to 0, which implies the value of our y is what, 0. Okay, now the L, we don't have any L over here, so the power is what, 0. So 0 is equal to what, x plus z. Okay, but then we have our z to be negative half, so it implies 0 is equal to what, s minus half. So which means our s is equal to what, positive half. Okay, so at the end of comparing powers, we were able to get that our z is equal to negative half, y is equal to 0, and then our x is what, positive half. Okay, then from here straight away we can go ahead and look at the relationship between our quantities. So let me get some space at the top over here. Okay, so whenever we are done with this, okay, we first of all need to, okay, let me get rid of this as well. Okay, so we first of all have to write this equation down again, and then we insert our powers, the values we have for x, y, and z over here. So we have our period is equal to k, then the L has the power what, x, so which is half, positive half y, so we write the half. Then the m has the power y, which is 0, and then the gravity has the power negative half. Okay, so from here m automatically becomes 1, so it doesn't really play any role again. So we have p is equal to what, k. Now the L will become 1 over L because it has the power, it will become root L. Okay, and then g raised to the power negative half becomes what, times 1 over what, root g. So if we further simplify this, we have period will be equal to what, k root of L divided by root of what, g. Okay, so this is the relationship between the period of oscillation and then the length, the gravity, and then the mass. So from here we can simply say that the period of oscillation does not depend on the mass, because at the end the mass is not in the equation over here, so they are not related. Okay, So the period does not depend on the mass, but then it depends on the root of the length, and then inversely proportional to what the root of the gravity. So this is how we solve a problem on dimensional analysis. Okay, so let's have a look at another example to further enhance our understanding of the concept. So let's have a look at example number 2. So this is example number 2. So for example number 2, they say the frequency F of a vibrating string depends on the length L of the string, the tension T in the string, and then the mass per unit length mu of the string. Derive an equation between what? The frequency, the length, the tension, and then mass per unit length, which is the mu. So let's have a look at our quantities we have in this example. So first of all, we have frequency, and then frequency is what? 1 over what? Time. Okay, so the dimensional equation for frequency, okay, is T inverse. Okay, so with that being said, let's go on and find the other terms that we have. So over here we have depends on the length. So we have L. The dimensional equation for L is still what? Length. So that one no problem. Now we have tension, which is T. Tension is a type of force. Okay, so once it's a type of force, it also has the same dimensional equation as force. So it is what? MLT minus 2, as we saw earlier on. And then the last one we are having over here is mu. Okay, mu we don't know, but they are saying is what? Mass per unit length, which means we have what? Mass over L per unit length, which means the dimensional equation for this is what? ML minus 1. Okay, so once we now have this, we can go on ahead and then what? Write the relationship between these quantities. So we have frequency, okay, being proportional to what? First of all, the length, then the tension, and then the mass per unit length. Okay, so once we remove the proportionalities and we introduce a constant, so we have F is equal to what? K L raised to the power X, T raised to the power Y, and then mu raised to the power Z. Okay, so from here let's input their dimensional equations to get what we want. So in place of F over here, we are going to put T inverse. So we have T inverse is equal to K L power X. For T we will have MLT minus 2 power Y. Then we have what? ML minus 1 power Z. So we expand this bracket. So we have T inverse is equal to what? K L power X. Then we have M power Y, L power Y, T negative 2Y. Then for this one we have M power Z, and then L negative Z. Okay, so from here we have L and then M common, so let's further simplify. So we have T inverse is equal to K. Then for the L we have L power X, then we have Y here, so plus Y, then negative Z here, so minus Z. Okay, so we have M power Y plus what? Z, which is over here. Then we have T negative 2Y. So from here we compare powers. So comparing powers. Okay, so now comparing powers, because we have T here, we have T here, let's go the easier way. So let's choose comparing powers of T first. Okay, so if you are comparing powers of T first, we have negative 1 will be equal to what? Negative 2Y. So we have negative 1 is equal to negative 2Y. Okay, which implies this is Y, which implies our Y is equal to what? Positive half. From here we move on to M. Comparing powers of M, we don't have any M here, so the power is 0 is equal to what? Y plus Z. But then the Y over here is what? Positive half. So we have what? 0 is equal to what? Half plus Z. This means if we make Z the subject, we will have what? Z to be equal to what? Negative half. Okay, that is, we maintain the Z over, and then we bring the negative the positive half across the equal to sign, it becomes negative. So from here we can now find L, the value of X. Okay, so over here we don't have any L, so the power is still 0. So we have 0 is equal to X, we don't know, but then we know Y to be what? Half, so plus half, then minus this negative sign, then into bracket. The Z we have is what? Negative half. Okay, so at the end this will become positive, so we have what? S plus 1, okay, is equal to 0. Okay, so which means our S is equal to a negative 1. So after solving for the values of x, y, and z, we have our x to be what? Negative 1, our y to be half, and then our z to be what? Negative half. Okay, so now that we have this, let's go ahead and then further deduce the relationship between our quantities. Okay, okay, so from here we still write the first equation we first wrote, and then we have our frequency is equal to what? K. Then the L has the power of x, which is negative 1. Then the T has the power of y, which is half. And then the mu, sorry, let me rewrite that well. Mu has negative 1 over 2. So which means from here we have F is equal to what? K. And L raised to the power negative 1 is 1 over L. Okay, so times T power half is what? Root T, and then times this will be what? 1 over root mu. So if we further simplify this, we have K over L root of what? T over what? Mu. Okay, so this is the relationship between the frequency, okay, of the vibrating string, the length, the tension, and then the mass per unit length. So it means the frequency over here is inversely proportional to the length, directly proportional to the root of the tension, and then inversely proportional to the root of the what? Mass per unit length. So this is how we use dimensional equation or dimensional analysis to find the relationship between quantities. Okay, now I hope we are all on the same page over here and we've gotten our answer if you are following along. Okay, so I can get rid of this. Okay, thanks. Now remember I said the third uses of dimensional analysis is the fact that they can be used to check the validity of an equation. Yes, let's have a very simple example about that. Okay, so we know this popular formula, that is v square is equal to what? U square plus 2as. Okay, now s, v, and then u are what? Velocities. Okay, and then by being velocities, okay, you have the dimensional analysis lt minus 1. V is the final velocity, u is the initial velocity. We have a is the acceleration, then acceleration has the dimension of what? Lt minus 2. Then we have s, which is the distance, so distance is length, so it has the dimension L. Okay, so let me put them in the bracket to show I'm talking about their dimension. Okay, so from here all we need to do is to substitute everything we have over here in place of the formula, and we get our answer. Okay, to prove that yes, this equation is actually valid. Okay, so we have the v, which is over here, so we have lt minus 1 squared is equal to another lt minus 1 squared plus 2 into bracket what? We have lt minus 2 times L. Okay, so we have over here, this is L squared t negative squared is equal to here L squared t negative squared plus the L times L over here will give us what? 2 into bracket L squared t negative squared. Okay, so we can see that we have L squared t negative squared over here, the same thing over here. So we can have L squared t negative squared is equal to what? This is, there's 1 here, there's 2 here, so we have 3 into bracket L squared t negative squared. Now can we see that on the left hand side and then the right hand side we have what? L squared t negative squared. Yes. Okay, in dimensional analysis, to check for the validity of an equation, okay, the coefficient of the dimensional analysis or the dimensional equations doesn't matter. Okay, so whether this is 4 or 5 or 1 over 3, it doesn't really matter, but once the dimensions are the same, we say the equation is valid. Okay, so in this example we have what? L squared t negative squared over here, and then over here we also have L squared t negative squared. So the equation is said to be what? Valid, because we have the same dimensions on both sides, irrespective of the coefficient on either side of the equation. So this is how we use dimensional analysis to check for the validity of an equation. I will encourage you to go and look for more examples and solve, so that you further enhance your understanding about dimensional analysis. So thank you very much for watching, and then I'll see you in the next video. Bye bye.